Welcome to lab report number 3 concerning black holes. In this lab, we know a star is orbiting a black hole of unknown mass. And we know the position information of the star in terms of its X and Y position data that's been gathered. And we know the stationary position of the black hole. And we were asked to attempt to use this information to determine the mass of the black hole. In order to do that, I intend to apply Newton's second law, particularly as the impulse momentum theorem. Now, to explain how I'm going to do that, I want to start with Newton's second law, and by rearranging algebraically, I end up with an expression that gives me a change in momentum being equivalent to the impulse applied to the object. And this is where we start to see that the forces applied over time to an object will result in changes in momentum. And we see that in these expressions on this page, where the change in momentum of an object is equivalent to the net force, only in terms of the units. The values are going to be the same, because momentum is mass times velocity, and over time that gives us kilograms meters per second squared. And forces are mass times acceleration, which is kilograms meters per second squared. So these two things are different, but their units and their values are equivalent. It is the action of forces that cause changes in momentum, and it's these changes in momentum that we can see and evaluate in this problem. So to see, now one past thing, if the changes in time of this momentum are small enough, they can closely approximate the derivatives. And so here you see the calculus that we apply, ultimately that our changes in momentum have two components, that they have a parallel component and a perpendicular component. The parallel component will tell us about the motion of the object and whether it's speeding up or slowing down. The perpendicular component will tell us about the curviness of the motion of the star. We can determine the radius between the star and the black hole using the position data that were provided. Now, before I show you the program, I also want to explain how I calculated the mass. I used the force on the star by the black hole expressed with Newton's universal law of gravitation, where g, or the gravitational constant, is multiplied by the mass of the star and the mass of the black hole, and divided by the magnitude of the radius squared between those two. Rearranging this formula, I determined the mass of the black hole to be 2.37 times 10 to the 31st kilograms. And I'd like to show you the code that was involved here. Starting with the system properties, I stated the mass of the star, position of the black hole, and the gravitational constant. Delta T was 60 seconds times 60 minutes in an hour times 24 hours in a day to give us a time step of a day stated in seconds. This is the code for how we use the list data to evaluate the change in position as well as the change in velocity. This is similar to the activity we did with the mystery motion of an object. In the calculation loop, here's the code for my initial and final velocities that we use to find the initial and final momentums. And here is where we state that the net force is equivalent to the changes in momentum over time, only in terms of their value being the same. Again, I want to iterate that it's these changes in momentum, the effects, are caused by forces. So the concept between those two is significantly different. We again have calculations for the parallel component and the perpendicular components of that. And down at the bottom we see my code for finding the mass of the black hole, shown here. Now, to be able to run this quickly, we run the module. We see that the program performs correctly. And I ask it to print at the bottom and give me information concerning the mass of the black hole, which it has done at the bottom. Now, so what if? We were asked one last question. I think I've answered the difference between change in momentum and forces. The thing we were asked is, what if we know, say, what we were asked, what if we have a, we were asked to assume if the motion of the observed star remains unchanged, could we tell the difference if it was a different black hole? And my answer would be no, it wouldn't. We would not be able to tell the difference, because if we have the same effects, they would have to be charged by the same forces, and these forces are due to the gravitational attraction. So if the motion of the star is unchanged, then the characteristics of the black hole would have to be this equivalent, and I would not be able to tell the difference between the two black holes. This concludes my results and my analysis for lab number 3. Thanks for listening.